Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. In the medieval Islamic world, mathematicians began to formalize something that had always existed implicitly: the concept of a procedure. A scholar named Muhammad ibn Musa al-Khwarizmi, working in 9th century Baghdad, wrote treatises that described methods for solving equations. He didn't just provide answers, he provided step-by-step processes that anyone could follow to reach those answers. His name, transliterated into Latin as algorithmi, would eventually give us the word algorithm. These algorithms were instructions for human minds, written in human language, but they possessed a quality that would prove essential. They were mechanical in nature. They said, do this, then this, then this. They made no appeals to intuition or creativity. They were recipes that worked every time, in every place, for every person who followed them correctly. For centuries, these procedures existed only on paper, executed only by human hands and minds. But paper and minds have limitations. They cannot scale. A calculation that takes one person an hour cannot be completed any faster by giving it to that same person again. And so, as human civilization grew more complex, as engineering projects became more ambitious, as astronomical tables became more detailed, as the machinery of commerce demanded ever more intricate accounting, the weight of calculation pressed down with increasing force. The European Renaissance brought with it a renewed interest in mechanical devices. Leonardo da Vinci sketched mechanical calculators, though they were never built in his lifetime. The wheels and gears that powered clocks suggested that perhaps calculation too could be automated. If you could build a machine to measure time's passage, why not build one to multiply numbers? In 1642, a young French mathematician named Blaise Pascal, watching his father labor over tax calculations, designed and built a mechanical calculator. The Pascaline, as it came to be called, used a series of numbered wheels connected by gears. Add a number, and the appropriate wheel would advance. When a wheel completed a full rotation, it would advance the wheel representing the next order of magnitude, the mechanical embodiment of carrying in addition. The device was beautiful in its way, a testament to precision craftsmanship, but it was also limited. It could add and subtract, but multiplication and division remained beyond its capacity. And it was expensive, so expensive that few were ever made. the world was not yet ready for automatic calculation. The infrastructure of precision manufacturing did not yet exist. The tolerances required for reliable mechanical computation exceeded what even skilled craftsmen could consistently achieve. 30 years later, Gottfried Wilhelm Leibniz improved upon Pascal's design, creating a machine that could multiply through repeated addition. But like Pascal's calculator, Leibniz's machine remained a curiosity, a demonstration of possibility rather than a practical tool. The Industrial Revolution had not yet arrived. The age of interchangeable parts, of precision machining, of mass production, all of that still lay decades in the future. And yet, in the design of these early calculators, in the careful arrangement of gears and wheels, a principle was being established, that mathematics could be embodied in physical form, that logical operations could be translated into mechanical operations, that the abstract could become concrete. The path toward artificial intelligence required more than mechanical calculators. It required a deeper question, one that would not be formally asked until the 19th century. What is computation itself? What does it mean to calculate? And could there be a universal machine, a device that could perform not just one specific calculation, but any calculation that could be specified? These questions emerged in an unlikely context, the weaving of fabric. In 1804, a French silk weaver named Joseph-Marie Jacquard developed a loom controlled by punch cards. Holes punched in stiff paper would determine which threads would be raised as the shuttle passed, creating complex patterns automatically. The loom operator didn't need to remember the pattern. The pattern was encoded in the cards themselves. This seems far removed from intelligence, from thought, from anything we might recognize as computation. But consider what Jacquard had created, a programmable machine. The cards were, in essence, instructions. Different cards produced different patterns from the same physical loom. The hardware remained constant, only the software, though that word would not be coined for more than a century, changed. Charles Babbage, an English mathematician working in the 1820s and 1830s, recognized the profound implications of Jacquard's invention. Babbage was frustrated by the errors in mathematical tables, logarithm tables, astronomical tables, navigation tables. These were computed by human computers, people, often women, who performed calculations by hand. The work was tedious, exhausting, and prone to mistakes. Ships were lost at sea because of errors in navigation tables. Engineering projects failed because of miscalculated stresses and loads. Babbage conceived of a machine he called the difference engine, a mechanical calculator that could compute polynomial functions automatically and print the results directly, eliminating transcription errors. He built a partial prototype, a beautiful assembly of brass gears and wheels, but the full machine was never completed. The precision required exceeded what 19th century manufacturing could reliably deliver. But Babbage didn't stop there. He envisioned something far more ambitious, the analytical engine. This machine would be programmable, controlled by punch cards like Jacquard's loom. It would have a store for holding numbers, what we would now call memory. It would have a mill for performing operations, what we would call a processor. It would be able to make decisions based on intermediate results, choosing different sequences of operations depending on what it calculated. Babbage never built the analytical engine. The technology of his era could not realize his vision. But in his notebooks and diagrams, he had described something that would not exist in physical form for more than a century: a general-purpose programmable computer. Ada Lovelace, working with Babbage, saw even further. In her notes on the analytical engine, she described something that Babbage himself had not fully articulated: that such a machine need not be limited to arithmetic. If you could represent something symbolically, music, for instance, or language, and if you could define operations on those symbols, then the machine could manipulate those symbols according to rules. It could, in her words, compose music or produce graphics. Lovelace had grasped a fundamental principle: that computation is not fundamentally about numbers, but about the manipulation of symbols according to rules. This insight would lie dormant for generations, but it would eventually become the foundation of everything that followed. The 19th century gave way to the 20th. Mechanical calculators became more sophisticated, more reliable, more common. Businesses used them, scientists used them, but they remained single-purpose devices, able to perform only the operations for which they were designed. The dream of a universal machine, of a device that could be instructed to perform any computation, remained unrealized. Then came the mathematical crisis of the early 20th century. Mathematicians had discovered paradoxes in the foundations of mathematics itself. Set theory, which seemed to provide a solid ground for all mathematical reasoning, contained contradictions. Bertrand Russell demonstrated that the naive concept of a set of all sets led to logical impossibility. Mathematics, it seemed, might not be as solid as everyone had assumed. In response, mathematicians began a program to formalize mathematics completely, to reduce it to a system of symbols and rules so rigorous that no contradictions could arise. David Hilbert, one of the greatest mathematicians of the age, proposed that all of mathematics could be built up from a small set of axioms through the mechanical application of logical rules. Every theorem could be proven or disproven through a finite sequence of steps. This was Hilbert's program, and it seemed achievable. Mathematics would become mechanical. Given enough time and patience, any mathematical question could be answered by following the rules. But in 1931, Kurt Gödel proved otherwise. His incompleteness theorems showed that any sufficiently powerful formal system would contain statements that were true, but could not be proven within the system. Mathematics could not be completely mechanized. There would always be truths that lay beyond the reach of mechanical proof. This might have been the end of the story of mechanical computation, a demonstration of its fundamental limits. But instead, the investigation into the nature of computation was just beginning. Because in trying to understand what could not be computed, mathematicians would finally define precisely what computation itself was. In 1936, a young British mathematician named Alan Turing published a paper titled On Computable Numbers. He was investigating the same questions that had concerned Hilbert. What can be computed? What does it mean for something to be computable? To answer these questions, Turing defined an abstract machine, not a physical device, but a mathematical concept. This machine would have an infinitely long tape divided into squares. Each square could contain a symbol. The machine would have a read-write head that could examine one square at a time, read the symbol there, write a new symbol, and move left or right along the tape. The machine would also have a finite set of states. At each step, based on its current state and the symbol it was reading, it would perform an action, write a symbol, move the head, and transition to a new state. The rules governing these actions, which symbol to write, which direction to move, which state to enter, would be specified in a table of instructions. This Turing machine, as it came to be called, was remarkably simple. It had only the most basic operations: read, write, move, change state. And yet, Turing proved that this simple machine could compute anything that could be computed. Any mathematical function that could be calculated by following a definite procedure could be calculated by a Turing machine with the appropriate table of instructions. Moreover, Turing showed that you could design a universal Turing machine, a machine whose instruction table was itself stored on the tape. This universal machine could simulate any other Turing machine. Give it the instruction table for another machine, and it would behave exactly as that machine would behave. One machine could become any machine. This was a profound insight. It meant that there was no need for a different physical device for each different computation. A single, universal machine could perform any computation, provided you gave it the right instructions. Hardware and software were separate. The same physical substrate could embody different logical processes. At almost the same moment, in Princeton, New Jersey, Alonzo Church was investigating the same questions using a different formalism called lambda calculus. Church's approach was purely symbolic, based on the manipulation of function definitions. It looked nothing like Turing's machine-based model. And yet, Church and Turing proved that their systems were equivalent. Anything computable in one was computable in the other. This equivalence suggested something deep, that there was a fundamental notion of computability that transcended any particular formalism. Whether you thought in terms of machines or functions, whether you used tapes and symbols or abstract algebra, you would arrive at the same class of computable functions. This notion came to be called the Church-Turing thesis, and it remains the foundation of computer science. But these were mathematical abstractions. They existed in papers, in the quiet spaces of university libraries. The world outside was moving toward war, and war would demand not abstract mathematics, but concrete machines. Machines that could calculate firing tables, decode encrypted messages, predict the trajectories of bombs. The Second World War accelerated the development of computing machinery in ways that peace never could. The calculations required for warfare, ballistics, cryptography, nuclear physics, exceeded what human computers could manage. Machines were needed urgently. In Britain, at Bletchley Park, a team of mathematicians and engineers built machines to break German encryption. The Germans used Enigma machines, mechanical devices that encrypted messages using rotors that scrambled letters in complex, constantly changing patterns. Breaking Enigma required testing thousands of possible rotor configurations, a task far beyond human capacity. Alan Turing, the same man who had defined the abstract concept of computation, now worked to build concrete computing machines. The bomb, as one such machine was called, used electromechanical relays to rapidly test potential Enigma settings. It was not a general-purpose computer. It was designed for one specific task, but it demonstrated that machines could perform logical operations at speeds impossible for humans. Later in the war, the British built Colossus, a machine that used vacuum tubes instead of relays. Vacuum tubes could switch on and off thousands of times faster than mechanical relays. Colossus was used to break an even more sophisticated German encryption system called Lorenz. It was programmable to a degree. Its function could be modified by rewiring panels and setting switches. It processed data at electronic speeds through the flow of electrons rather than the movement of mechanical parts. Colossus was kept secret for decades after the war. Its existence was not publicly acknowledged until the 1970s. And so, for many years, the first electronic computer was believed to be ENIAC, the electronic numerical integrator and computer, built in the United States. ENIAC was enormous. It occupied a large room, contained 18,000 vacuum tubes, weighed 30 tons, and consumed enough electricity to power a small neighborhood. It generated so much heat that it required industrial cooling fans. Tubes burned out regularly, requiring constant maintenance. But it could perform calculations at unprecedented speed. A trajectory calculation that would take a human computer 20 hours could be completed by ENIAC in 30 seconds. Like Colossus, ENIAC was programmed by physically rewiring it. Cables had to be unplugged and replugged to change its function. Setting up a new calculation could take days. It was a computer, but it was not yet a stored program computer. A machine where the instructions themselves resided in memory, changeable as easily as data. The transition from calculating machine to stored program computer required one more conceptual leap, and that leap came from a mathematician who had spent the war years working on the atomic bomb project. John von Neumann, a Hungarian-born prodigy who had made contributions to quantum mechanics, game theory, and pure mathematics, became involved with the ENIAC project near its completion. Von Neumann immediately grasped the limitations of a machine that had to be rewired for each new task. He proposed a different architecture: store both the program and the data in the same memory. The computer would read instructions from memory, execute them, and write results back to memory. Programs could be modified just as easily as data. A computer could even modify its own instructions as it ran. This architecture, now called the von Neumann architecture, became the template for nearly every computer built over the next 70 years. The details would change, components would shrink, speeds would increase by factors of millions, but the fundamental organization remained: a processing unit that executes instructions, a memory that stores both instructions and data, and a bus that connects them. The first stored program computers were built in the late 1940s. The Manchester Baby in Britain, 1948. The EDSAC in Cambridge, 1949. The UNIVAC in the United States, 1951. These machines still used vacuum tubes. They still filled entire rooms. They still required teams of specialists to maintain them. But they could run different programs without rewiring. Software had become truly separate from hardware. The vacuum tube era lasted about a decade. Tubes were fragile, power-hungry, heat-generating. Large computers required thousands of them, and the probability that at least one would fail in any given hour was uncomfortably high. Computing was possible, but it was expensive and unreliable. The solution came from a different domain entirely: the quest to improve radios and telephone systems. In 1947, researchers at Bell Telephone Laboratories invented the transistor, a solid-state device made of silicon that could amplify electrical signals or act as an on-off switch. Transistors were smaller than vacuum tubes, more reliable, more efficient. They generated far less heat. They could be manufactured more consistently. By the late 1950s, transistors began replacing vacuum tubes in computers. The IBM 7090, released in 1959, used transistors throughout. It was smaller, faster, and more reliable than its vacuum tube predecessors. The age of discrete transistors had begun, though it would be brief, because already engineers were envisioning the next step: putting multiple transistors on a single piece of silicon. The integrated circuit emerged from the realization that if you could create one transistor on a silicon wafer, you could create many. You could etch entire circuits, transistors, resistors, capacitors, the connections between them, onto a single chip of silicon using photographic techniques. The circuit would be integrated, all its components part of a single piece of material. Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor independently developed integrated circuits in 1958 and 1959. Early chips contained only a few components, but the technology improved rapidly. By the mid-1960s, chips contained dozens of transistors. By the early 1970s, hundreds. By the end of the 1970s, thousands. This scaling followed a pattern that Gordon Moore, co-founder of Intel, had observed in 1965. Moore noted that the number of transistors that could economically fit on a chip seemed to double approximately every 2 years. This observation, later called Moore's Law, held true for decades. It was not a law of nature, but a description of human ingenuity, of engineers finding ways to make features smaller, to pack components tighter, to improve yields and reduce defects. The miniaturization of computing hardware changed what computers could be used for. The machines of the 1950s had been confined to research laboratories, military installations, and the largest corporations. They required climate-controlled rooms, specialized electrical infrastructure, trained operators. But as computers shrank and became cheaper, new possibilities emerged. In 1971, Intel released the 4004, a complete computer processor on a single chip. It had been designed for a calculator, but it was a general-purpose device. It could execute any program. 4 years later, the first personal computers appeared. Hobbyist machines sold as kits that enthusiasts assembled in their garages and basements. These early personal computers were crude by modern standards. They had tiny amounts of memory. They displayed only text, no graphics. They had no hard drives. Programs and data were stored on cassette tapes. But they demonstrated that computing need not be centralized. A computer could sit on a desk. An individual could own one. Throughout the 1970s and 1980s, personal computers evolved. Memory increased. Graphics capabilities improved. Floppy disk drives and eventually hard drives provided faster storage. User interfaces shifted from command lines to graphical windows. The machines became more accessible, requiring less specialized knowledge to operate. But these were still primarily calculation machines. They could process numbers, manipulate text, store information. They could be programmed to follow instructions, but they could not learn. They could not adapt. They could not recognize patterns they had not been explicitly programmed to recognize. They were not, in any meaningful sense, intelligent. For that, a different approach would be needed, and the seeds of that approach had actually been planted decades earlier, in the 1940s, in the work of neurophysiologists trying to understand the brain. Warren McCulloch was a neurophysiologist. Walter Pitts was a mathematical prodigy. In 1943, they published a paper proposing a mathematical model of neurons, the cells that make up the brain and nervous system. In their model, each neuron received inputs from other neurons. If the sum of those inputs exceeded a certain threshold, the neuron would fire, sending a signal to neurons connected to it. This simple model captured what seemed to be the essential behavior of real neurons. They accumulated signals from their inputs and activated when those signals reached a sufficient level. McCulloch and Pitts showed that networks of these simplified neurons could perform logical operations. A network could be wired to compute and, or not, the basic functions of Boolean logic. In fact, any function that could be computed by a Turing machine could be computed by a sufficiently large network of these artificial neurons. This suggested a tantalizing possibility. Perhaps intelligence could emerge from networks of simple processing units, each performing a trivial computation, but collectively producing complex behavior. Perhaps the brain's power came not from any individual neuron's sophistication, but from the vast number of neurons and the intricate patterns of their connections. This idea lay dormant for years. The computers of the 1940s and 1950s were too small, too slow to simulate neural networks of interesting size. And besides, the dominant paradigm in computer science was symbolic artificial intelligence. The idea that intelligence consisted of manipulating symbols according to logical rules. Symbolic AI achieved early successes. In 1956, Alan Newell and Herbert Simon created the logic theorist, a program that could prove mathematical theorems by searching through possible sequences of inference rules. The following year, they created the general problem solver, intended to solve a wide variety of problems using the same search-based approach. These programs demonstrated that machines could perform tasks that seemed to require intelligence, proving theorems, solving puzzles, playing games. In 1997, IBM's Deep Blue would defeat world chess champion Garry Kasparov, searching through millions of possible move sequences to find optimal plays. But symbolic AI had limitations. It worked well for problems that could be precisely defined, where the rules were known, where all relevant information could be represented symbolically. It struggled with tasks that humans found easy, recognizing faces, understanding natural language, navigating cluttered environments. These tasks seem to require not logical reasoning, but pattern recognition, the ability to perceive similarity, to generalize from examples, to handle ambiguity and noise. Neural networks offered a different approach to these problems. Instead of programming explicit rules, you would train a network on examples. You would show it many instances of the patterns you wanted it to recognize, and the network would adjust its internal connections to better match those examples. Learning, not programming, would give the network its capabilities. In 1958, Frank Rosenblatt at Cornell Aeronautical Laboratory built the perceptron, one of the first neural network machines. It had photoelectric cells as inputs, connected through randomly wired connections to output units. By adjusting the strength of these connections based on whether the network's output was correct or incorrect, the perceptron could learn to recognize simple visual patterns. Rosenblatt was optimistic, perhaps overly so. He suggested that perceptrons would soon be able to recognize speech, learn languages, make decisions. The Navy funded a machine called SNARC, Stochastic Neural Analog Reinforcement Calculator, that embodied these principles in hardware. But the limitations of simple neural networks soon became apparent. In 1969, Marvin Minsky and Seymour Papert published Perceptrons, a mathematical analysis showing that single-layer neural networks could not learn certain simple functions. The XOR function, which outputs true when its inputs differ, could not be computed by a single-layer perceptron. The book was technically correct, but arguably overly pessimistic about the prospects for multi-layer networks. Funding for neural network research dried up. The 1970s and early 1980s became known as the AI winter, a period when progress seemed stalled, when the grand promises of artificial intelligence seemed unlikely to be fulfilled. Research continued, but quietly, out of the spotlight. The breakthrough came in 1986, when David Rumelhart, Geoffrey Hinton, and Ronald Williams published a paper describing the backpropagation algorithm. Backpropagation provided an efficient way to train multi-layer neural networks. The algorithm calculated how much each connection in the network contributed to the network's errors, and adjusted those connections to reduce those errors. With backpropagation, neural networks could learn complex functions. They could learn to recognize handwritten digits, to compress data, to predict time series. They could be trained on examples without requiring humans to specify explicit rules. The capabilities that had eluded symbolic AI, pattern recognition, generalization, robustness to noise, came naturally to trained neural networks. But there were still limitations. Training neural networks required substantial computational power. The networks needed large amounts of training data. And even with backpropagation, training deep networks with many layers between input and output, proved difficult. Errors calculated at the output would diminish as they propagated back through the layers, making it hard to adjust the early layers effectively. These limitations kept neural networks from dominating AI research through the 1990s and early 2000s. Other approaches support vector machines, decision trees, ensemble methods, often worked better with the limited data and computational resources available. Neural networks were one tool among many, useful for certain problems, but not universally superior. All of that would change in the 2010s, when three factors converged: much larger datasets, much more powerful computers, and algorithmic innovations that made training deep networks practical. The internet had been growing since the 1970s, but it remained a tool for researchers and enthusiasts until the early 1990s, when the World Wide Web made it accessible to the general public. In the 2 decades that followed, an enormous amount of data accumulated online: text, images, videos. This data was often publicly accessible, and it could be used to train machine learning systems. Meanwhile, computer processors had continued to follow Moore's law, becoming exponentially faster. But speed was not the only relevant factor. In the 2000s, researchers discovered that graphics processors, chips originally designed to render video game graphics, were well suited to the mathematical operations required for training neural networks. GPUs, as these graphics processing units were called, could perform many calculations in parallel, dramatically accelerating the training process. The algorithmic innovations were more subtle. Researchers developed better initialization methods for neural networks, ways to set the initial random weights so that training would proceed more smoothly. They developed new activation functions, the mathematical operations applied at each neuron, that avoided some of the problems that had plagued earlier networks. They developed regularization techniques to prevent networks from memorizing training data rather than learning general patterns. In 2012, these factors came together dramatically at the ImageNet competition, an annual contest to build systems that could classify images into one of 1,000 categories. Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton entered a deep neural network, 8 layers deep, trained on GPUs using a large labeled image dataset. Their system achieved an error rate of 15.3% compared to 26.2% for the next best entry. The improvement was stunning, unmistakable. That result marked the beginning of the deep learning era. Over the next few years, deep neural networks came to dominate not just image recognition, but speech recognition, machine translation, game playing. Tasks that had resisted decades of AI research suddenly became tractable. The networks grew deeper. Architectures like ResNet used 50, 101, even 152 layers. The networks grew wider, with millions of parameters to be learned from data. Training required days or weeks on specialized hardware, using datasets containing millions of examples. But the results were extraordinary. Neural networks learned to recognize objects in images with accuracy approaching human performance. They learned to transcribe speech, to translate between languages, to generate realistic images from text descriptions. In 2016, DeepMind's AlphaGo defeated the world champion in Go, a game long considered too complex for computers to master. AlphaGo used deep neural networks to evaluate board positions and select moves. These systems were not programmed with explicit rules. They learned patterns from data. They learned representations, internal structures that captured the statistical regularities in their training data. Early layers in an image recognition network learn to detect edges and textures. Middle layers learn to detect parts, wheels, eyes, leaves. Later layers learn to detect whole objects, cars, faces, trees. These representations emerged from training. No human specified them. The architecture that proved most transformative, however, was the transformer, introduced in 2017 by researchers at Google. Transformers processed sequences, text, for instance, by allowing each element of the sequence to attend to every other element. This attention mechanism enabled the network to capture long-range dependencies, to understand how words at different positions in a sentence related to each other. Transformers could be trained on massive text corpora, learning to predict the next word in a sequence. This simple training objective, predict the next word, led to networks that learned grammar, learned facts about the world, learned to perform reasoning tasks. They learned, in some sense, a statistical model of human language and the knowledge embedded in text. By 2018, models like BERT and GPT demonstrated that transformers pre-trained on large text corpora could be fine-tuned for specific tasks with relatively small amounts of additional training data. They could answer questions, summarize documents, translate languages. The quality of their outputs improved as the models grew larger, more layers, more parameters, more training data. In 2020, OpenAI released GPT-3, a model with 175 billion parameters, trained on hundreds of billions of words. GPT-3 could generate coherent text on almost any topic. It could write stories, answer questions, write code, engage in conversation. It was not perfect. It made errors, sometimes confidently asserting falsehoods. But its capabilities were qualitatively beyond what had come before. These large language models, as they came to be called, represented a form of artificial intelligence quite different from the symbolic AI of earlier decades. They did not manipulate symbols according to logical rules. They did not have explicit knowledge bases. Instead, they embodied patterns learned from vast amounts of text, patterns that enabled them to generate plausible continuations of any input they received. The neural networks of the 2000s and 2000s also extended beyond language. Networks learned to generate realistic images from text descriptions. They learned to generate music, to synthesize speech in any voice, to predict protein structures. They learned to play video games at superhuman levels, to control robots, to optimize complex systems. Each of these applications required different architectures, different training procedures, different data sets. But they shared a common principle. They learned from data. They found patterns in examples. They generalized from what they had seen to what they had not. This approach, learning rather than programming, had become the dominant paradigm in artificial intelligence. Today, artificial intelligence systems operate continuously, quietly, in the infrastructure of daily life. When you speak to a voice assistant, a neural network transcribes your speech, and another network interprets your intent. When you search for information, networks rank the results, attempting to predict which will be most relevant. When you watch a video online, networks predict what you might want to watch next. These systems do not announce themselves. They process requests in milliseconds, in data centers distributed across continents. The computation happens far from the user, on specialized hardware optimized for the mathematical operations that neural networks require. The results flow back across fiber optic cables, across wireless networks, arriving so quickly that the delay is imperceptible. The infrastructure supporting these systems is vast. Training large neural networks requires enormous amounts of computation, calculations that would take centuries on a single computer complete in days or weeks when distributed across thousands of specialized processors. The training happens once or periodically as new data becomes available. The trained model is then deployed, copied to many machines that serve requests in parallel. Inference, using a trained model to process new inputs, requires less computation than training, but must happen quickly. A user speaking to a voice assistant expects a response within seconds. A user searching for information expects results immediately. To achieve this responsiveness, the models are optimized, simplified, compressed. Techniques like quantization reduce the precision of the model's parameters. trading slight reductions in accuracy for large improvements in speed. The systems are monitored continuously. Engineers track error rates, latencies, resource usage. They test new model versions, gradually rolling them out while comparing their performance to existing versions. They collect data on failures, on cases where the model produces incorrect or inappropriate outputs. This data feeds back into the training process, helping to improve future versions. The entire pipeline, data collection, data cleaning, model training, evaluation, deployment, monitoring, has become systematized. Tools and frameworks abstract away much of the complexity. Researchers can experiment with new architectures without implementing all the low-level details. Engineers can deploy models without understanding all the mathematics underlying them. The field has matured to the point where artificial intelligence systems can be built and maintained by teams, not just by individual experts. But the systems are not autonomous. They do not set their own goals. They optimize objectives specified by humans. Predict the next word accurately. Classify this image correctly. Translate this sentence faithfully. Within those objectives, they find patterns, develop representations, make predictions. But the objectives themselves come from outside. These systems also have limits that are not always apparent. They excel at pattern recognition, at finding statistical regularities in data, but they struggle with tasks that require understanding causality, with reasoning about hypothetical scenarios that differ systematically from their training data, with tasks that require maintaining and manipulating complex mental models. A language model can generate fluent text on nearly any topic, but it does not understand the text in the way a human does. It does not have a model of the world that it consults. It does not reason step by step, though it can generate text that looks like step-by-step reasoning. It finds patterns in sequences of words, and those patterns enable impressive capabilities. But the capabilities have boundaries. Image recognition systems can identify objects with high accuracy, but they can be fooled by adversarial examples, carefully constructed images that look normal to humans, but cause the network to make confident, completely wrong predictions. The networks have learned to recognize patterns in natural images, but those patterns do not correspond perfectly to the semantic categories humans use. Neural networks trained on historical data can perpetuate biases present in that data. If a hiring system is trained on data from a company that historically hired more men for certain positions, the system may learn to favor male candidates, not because it was programmed to discriminate, but because it learned patterns that reflect past discrimination. These limitations are not mere engineering challenges to be solved by making networks larger or training them on more data. They reflect fundamental characteristics of learning from examples. A system trained to optimize a particular objective on a particular dataset will excel at tasks similar to those in its training data and struggle with tasks that differ in systematic ways. Understanding these limitations is crucial for deploying AI systems responsibly. The systems are tools, powerful tools, but tools nonetheless. They augment human capabilities, but do not replace human judgment. They can process vast amounts of data, recognize subtle patterns, make predictions at scale, but they cannot set priorities, cannot weigh conflicting values, cannot take responsibility for their decisions. And so, the infrastructure of artificial intelligence is not just technical. It includes policies, guidelines, review processes. It includes human oversight, human judgment, human accountability. The systems operate quietly, continuously, but always within structures created and maintained by people. The artificial intelligence systems operating today are not isolated. They are connected components in a global computational infrastructure. Data flows continuously between devices and data centers. Models trained in one location are deployed across thousands of servers worldwide. Requests from users on every continent are routed to nearby servers to minimize delay. This infrastructure operates at scales difficult to comprehend. Every second, billions of queries are processed. Searches, translations, recommendations, predictions. Each query involves millions of mathematical operations, executed on silicon chips containing billions of transistors. The electricity consumed by data centers amounts to a measurable fraction of global power generation. The infrastructure is layered. At the lowest level, transistors switch on and off, electrons flowing through carefully designed circuits. Above that, processors execute instructions, accessing memory, performing calculations. Above that, operating systems manage resources, scheduling tasks, moving data. Above that, frameworks handle the mathematics of neural networks, the tensor operations that implement learning and inference. Higher still, applications coordinate these components, assembling complex behaviors from simpler ones. A voice assistant might use one network to transcribe speech, another to pass the transcription into a structured query, another to retrieve relevant information, and yet another to generate a natural language response. Each network is a component in a larger system. The systems communicate across networks that span the globe. Fiber optic cables carry light pulses across ocean floors, connecting continents. Satellites relay signals to remote regions. Cellular towers enable wireless access. Routers direct traffic, ensuring data reaches its destination, even as the network topology shifts. This infrastructure did not appear suddenly. It accumulated gradually, each component building on earlier layers. The transistors that enable modern processors descend from the vacuum tubes of the 1940s. The networks that carry data descend from telephone networks. The software frameworks descend from programming languages developed in the 1950s. The neural network architectures descend from mathematical models proposed in 1943. Each generation of researchers and engineers inherited the tools and concepts of the previous generation, extended them, refined them, combined them in new ways. The progress was not smooth. There were dead ends, periods of stagnation, sudden breakthroughs. But over decades, capabilities accumulated. Problems that were once intractable became routine. The development was not inevitable. It required sustained investment, coordination across institutions, the patient work of thousands of people. It required theoretical insights and practical engineering. It required both competition and collaboration, both individual creativity and collective effort. And it is not complete. The systems operating today will be replaced by more capable systems. Architectures will evolve. Training methods will improve. New applications will emerge. The boundaries of what can be learned from data will expand. Some of the coming developments are predictable. Networks will continue to grow larger, as long as doing so improves performance and the necessary computational resources are available. Training will become more efficient, enabling faster experimentation. Specialized hardware will continue to emerge, optimized for the specific operations that neural networks require. Other developments are harder to foresee. New architectures may emerge that learn more efficiently from smaller amounts of data. Methods may be developed that enable networks to reason more systematically, to maintain and update explicit models of the world. Systems may learn to combine the pattern recognition capabilities of neural networks with the logical reasoning of symbolic AI. The systems may become more interpretable, their internal representations and decision processes more transparent, or they may become more opaque as the networks grow larger and more complex. The trade-offs between performance, efficiency, interpretability, and robustness will continue to be explored. What seems clear is that artificial intelligence will become more integrated into the infrastructure of daily life. More decisions will be informed by predictions from machine learning systems. More processes will be optimized by algorithms trained on data. More interfaces will adapt to individual users, learning from their behavior. This integration raises questions that are not purely technical. Questions about privacy, about fairness, about accountability. Questions about what tasks should be automated and what tasks require human judgment. Questions about how to ensure that these powerful tools serve broad interests rather than narrow ones. These questions do not have purely technical answers. They require ethical reasoning, political deliberation, ongoing negotiation among stakeholders with different values and interests. The infrastructure of artificial intelligence is not just cables and chips and code. It is also policies and norms and institutions, social structures that shape how the technology is developed and deployed. Artificial intelligence emerged from a question: can machines think? That question, posed most famously by Alan Turing in 1950, has never been definitively answered. Perhaps it cannot be, because thinking itself is not precisely defined. But in pursuing that question, in attempting to build machines, that could perform tasks associated with intelligence, researchers created something real and consequential. They created systems that learn from data, that find patterns, that make predictions. These systems do not think in the way humans think. They do not have consciousness, emotions, intentions. They do not understand in the way humans understand. But they perform tasks that, when performed by humans, are considered intelligent. This raises a philosophical puzzle. If a system can answer questions, engage in conversation, solve problems, but does so by manipulating statistical patterns rather than by reasoning in any recognizable sense, is it intelligent? Or is it merely simulating intelligence, producing behaviors that look intelligent without any underlying understanding? Perhaps this is the wrong question. Perhaps intelligence is not a single thing, but a collection of capabilities: pattern recognition, memory, reasoning, language, planning. A system might possess some of these capabilities without others. It might be superhuman in pattern recognition, but limited in reasoning. It might generate fluent language without having anything like human understanding. The systems we have built are narrow. They excel at specific tasks for which they have been trained. A network trained to recognize images cannot translate languages. A network trained to play chess cannot diagnose diseases. Each system is a specialist, optimized for a particular domain. Human intelligence is general. Humans can learn to perform a vast range of tasks, can transfer knowledge from one domain to another, can reason about abstract concepts never directly experienced. We understand analogies, learn from a few examples, imagine counterfactuals. Whether artificial systems will develop these capabilities remains uncertain. Some researchers believe that general artificial intelligence, systems with the broad, flexible intelligence of humans, will emerge as narrow systems continue to improve. They argue that many of the same mechanisms that enable narrow intelligence can be scaled and combined to produce general intelligence. They point to the rapid progress of recent years as evidence that no fundamental barriers remain. Others are skeptical. They argue that current approaches, based on learning statistical patterns from data, are fundamentally limited. They suggest that general intelligence requires explicit reasoning, symbolic manipulation, compositional understanding, capabilities that neural networks do not naturally possess. They believe that new architectures, new training methods, perhaps entirely new approaches will be needed. The uncertainty extends to questions of risk and benefit. Artificial intelligence systems are already consequential. They influence what information people see, what opportunities they are offered, what decisions are made about them. As the systems become more capable, their influence will grow. This influence can be positive. AI systems can accelerate scientific research, discovering patterns in data that humans would miss. They can improve medical diagnosis, identifying diseases earlier and more accurately. They can make infrastructure more efficient, reducing waste and environmental impact. They can make information more accessible, translating languages, transcribing speech, describing images for those who cannot see them. But there are risks. Systems trained on biased data can perpetuate and amplify those biases. Systems optimized for engagement can amplify outrage, spread misinformation, polarize communities. Systems given poorly specified objectives can pursue those objectives in unexpected and harmful ways. Autonomous systems, drones, vehicles, weapons, can cause harm if they malfunction or are misused. Longer-term risks are more speculative, but potentially more severe. If artificial general intelligence is developed, and if such systems can improve their own capabilities, they might rapidly become far more capable than humans in ways that are difficult to predict or control. Ensuring that such systems remain aligned with human values becomes a critical challenge. These concerns are not reasons to halt research. Knowledge cannot be unlearned. Discoveries cannot be unmade. But they are reasons to proceed thoughtfully, to develop not just capabilities, but also safeguards. To ask not just what can be built, but what should be built and how it should be governed. The development of artificial intelligence has been a collective endeavor, spanning decades and involving thousands of researchers and engineers. It has been driven by curiosity, by practical needs, by competition, by the simple human desire to build things and understand things. It has produced tools that are genuinely useful, that improve lives, that solve problems. But like any powerful technology, it is not inherently beneficial or harmful. Its impact depends on how it is used, on the objectives it is given, on the context in which it is deployed. It depends on choices made by people, researchers, engineers, policymakers, users. Those choices will shape whether artificial intelligence amplifies human flourishing or exacerbates human problems. The trajectory of artificial intelligence points toward greater integration, greater ubiquity, greater capability. The systems will become faster, more accurate, more efficient. They will handle more modalities: text, image, sound, video, sensor data. They will operate in more domains: medicine, science, education, transportation, manufacturing, governance. The interfaces will become more natural. Instead of typing commands or clicking icons, people will speak, gesture, perhaps simply think. The systems will understand context, anticipate needs, adapt to individual preferences. The boundary between human and machine activity will blur as cognitive tasks are increasingly shared between biological and artificial intelligence. The systems will become more embedded, more invisible. They will operate not on separate devices, but within the infrastructure itself, in vehicles, buildings, factories, utilities. They will monitor and optimize, adjusting in real time to changing conditions. They will predict failures before they occur, route resources efficiently, minimize waste. This integration will be gradual. It will not happen all at once. Each application will be deployed separately, tested, refined. The systems will coexist with older technologies, with human processes, with analog methods. The transition will be uneven, faster in some domains and regions than others. But over time, the presence of artificial intelligence in daily life will deepen. Not dramatically, not visibly, but steadily. Tasks that once required human attention will be automated. Processes that once required human judgment will be informed by machine predictions. Decisions that once required human expertise will be assisted by systems trained on vast amounts of data. This future raises questions about work, about purpose, about meaning. If machines can perform cognitive tasks previously reserved for humans, what role remains for human intelligence? If systems can learn, create, decide, what distinguishes human cognition from artificial cognition? Perhaps the answer is that humans remain the source of values, of objectives, of meaning. Machines optimize functions, but humans define what should be optimized. Machines find patterns, but humans decide which patterns matter. Machines produce outputs, but humans judge what is valuable, what is beautiful, what is good. Or perhaps the distinction itself will evolve. As artificial systems become more sophisticated, as they develop capabilities that currently seem uniquely human, our understanding of intelligence, consciousness, and agency may shift. We may come to see intelligence as a spectrum rather than a binary, a property that can be possessed in different forms and degrees. The long-term future of artificial intelligence is fundamentally uncertain. We cannot know whether current approaches will lead to general intelligence or whether they will plateau, requiring fundamentally new ideas. We cannot know how quickly capabilities will improve or what their ultimate limits might be. We cannot know what new applications will emerge or what unintended consequences will arise. What we can know is that the trajectory is not predetermined. The future of artificial intelligence will be shaped by choices. Choices about what to build, how to train it, what objectives to give it, what safeguards to implement, what uses to enable, and what uses to prohibit. Those choices will be made by people working in research labs, in companies, in government agencies, in standards bodies. They will be informed by technical considerations: what is possible, what is efficient, what is reliable. But they should also be informed by ethical considerations, by an understanding of values and priorities, by a concern for consequences. The development of artificial intelligence is not merely a technical project. It is also a social project, one that requires ongoing deliberation, negotiation, adaptation. It requires institutions that can provide oversight, that can identify and address harms, that can ensure broad participation in decisions about how these powerful tools are developed and deployed. It requires humility, an acknowledgement that our predictions may be wrong, that unintended consequences may arise, that what seems beneficial in one context may prove harmful in another. It requires a willingness to learn from experience, to adjust course as we gather more information about how these systems behave in the world. And perhaps most importantly, it requires maintaining human agency. The systems should serve human purposes, not the other way around. They should augment human capabilities, not replace human judgment. They should be tools that people control, not autonomous agents pursuing their own objectives. This is not a given. It requires conscious effort, deliberate design, ongoing vigilance. It requires keeping humans in the loop, ensuring that important decisions are not delegated entirely to systems that may not understand context or consequences. It requires building systems that are transparent enough to be understood, predictable enough to be trusted, and aligned closely enough with human values to be safely deployed. The story of artificial intelligence is not finished. It is not even clear how far along in the story we are. Whether we are at the beginning, with general intelligence still far in the future, or whether we are further along than we realize, with major transitions approaching. What is clear is that artificial intelligence has moved from speculation to reality, from laboratory curiosity to infrastructure. The systems are no longer hypothetical. They are operating continuously, processing billions of requests, making predictions that influence outcomes. They are embedded in systems we depend on. This transition happened gradually, without fanfare, without singular moments that changed everything. It happened through the accumulation of small improvements, the patient refinement of techniques, the steady increase in data and computational power. It happened through the work of researchers and engineers who saw problems that needed solving and built tools to solve them. The systems we have built are impressive but limited. They excel at pattern recognition but struggle with reasoning. They can process vast amounts of data but cannot understand context the way humans do. They can optimize defined objectives but cannot set objectives themselves. They are powerful tools, but they are tools requiring human guidance and oversight. As the capabilities continue to expand, as the systems become more integrated into daily life, the questions become more pressing. How do we ensure that these systems are beneficial? How do we prevent them from perpetuating biases or causing harm? How do we maintain human agency and judgment in a world increasingly mediated by algorithms? These are not questions with simple answers. They require ongoing dialogue, experimentation, adaptation. They require engaging with different perspectives, different values, different concerns. They require institutions that can coordinate across borders, across sectors, across stakeholder groups. But they are questions worth asking, worth struggling with. Because artificial intelligence, for all its limitations and uncertainties, represents something genuinely new. Not in kind, perhaps, but in scale and scope. The capacity to learn from data, to recognize patterns, to make predictions at speeds and scales beyond human capability. These capacities open possibilities that previous generations could not have imagined. What we do with those possibilities will depend on choices made over the coming years and decades. Choices about what to build and what to forbid. Choices about how to distribute benefits and how to mitigate harms. Choices about how to preserve human agency in a world of increasingly capable machines. The path forward is not predetermined. The future of artificial intelligence will be shaped by human decisions, human values, human priorities. It will be shaped by technical advances, yes, but also by social institutions, by legal frameworks, by ethical norms. It will be shaped by conversations like this one, thoughtful, careful examinations of what has been built and what remains to be decided. In the quiet spaces between one era and the next, in the moments when old ways give way to new, there is always uncertainty. We cannot know precisely where we are headed. We can only observe where we have been, understand the mechanisms we have built, and make our best judgment about how to proceed. The systems will continue to evolve. They will become more capable, more integrated, more present in the infrastructure of daily life. That evolution will create opportunities and challenges, benefits and risks. It will require ongoing attention, ongoing adaptation, ongoing care. But for now, in this moment, we can observe what has been quietly made over decades of patient work, from abstract mathematical models to physical machines, from vacuum tubes to transistors to integrated circuits, from symbolic reasoning to statistical learning, from laboratory experiments to global infrastructure, each step building on the last, each generation of researchers and engineers inheriting tools and concepts from the previous generation, extending them, refining them, combining them in new ways. Each small advance contributing to capabilities that, in aggregate, have transformed what machines can do. This is what has been made. Systems that learn from data, that recognize patterns, that make predictions. Systems that process language, that understand images, that generate text and sound and video. Systems that optimize, that adapt, that improve with experience. Not intelligent in the way humans intelligent, but capable nonetheless of tasks that humans have historically performed. These systems operate continuously, quietly, in data centers distributed across the planet. They process queries, translate languages, recommend content, assist with decisions. They are infrastructure now, as essential to modern life as electricity or telecommunications. And like those earlier infrastructures, they are maintained by people, governed by policies, shaped by choices. As we leave the history of this system behind, let the weight of its complexity fade, leaving only the steady rhythm of your breath. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.